Okay, right. So right now we are going to talk about what is called synchronous machines. Okay, so 8.1, I'm just going to read the introduction. It says here, in synchronous machines, okay, the armature winding either exports AC power. Simply meaning we are talking about an AC alternator. Now this is important, nah? In synchronous machines, the armature winding either exports AC power or it imports AC power. Now, from my understanding, meaning the little that I know with regards to synchronous machines, is when we say export or import AC power, it's normally three phase. Three phase simply meaning if it's a motor, then this is not the correct word, but I'll use this word anyway. You inject three phase power. When I say three phase, I'm obviously referring to industry. Okay, right. Then you extract, when it is a generator, you extract three phase power. Okay, right. Synchronous alternator, synchronous motor, right. Okay, then it continues by saying, whereas the field winding is always energized, okay, always energized from a DC source. Now that makes sense, because normally what you are looking for now is you are looking for what we call an electromagnet. Okay, an electromagnet. And then this electromagnet, it's as the name says, it's a magnetic field that you induce using an electrical conductor, in this case a coil. Okay, and then you don't want an oscillating magnetic field, you want a stable magnetic field, and hence you supply DC. Okay, right. So that part should be clear. In synchronous machines, the armature winding either exports AC power, making it a synchronous alternator, or it imports AC power, okay, making it a synchronous motor, whereas the field winding is always energized from a DC source. Okay, right. In other words, a synchronous machine is a doubly excited energy conversion device. Okay, the generation of EMF in general depends on the relative motion between field flux and armature winding. The generation of EMF in general depends on the relative motion. Okay, relative motion. Relative motion, it means the motion of two or more objects relative to each other. Okay, the generation of EMF in general depends on the relative motion between the field flux and armature windings, between field flux and armature winding. Okay, in view of this, an AC generator, alternator, or synchronous generator may either have rotating field poles and a stationary armature, or a rotating armature and stationary field poles. Now let's just read that again, because that's too much. The generation of EMF in general, okay, it depends on the relative motion between field flux, okay, and armature windings. Okay, in view of this, an AC generator, simply meaning an alternator, or what we call a synchronous generator, may either have rotating field poles and the stationary armature. Okay, that's a generator. What is a generator? A generator is what? It states here, nah, it has either rotating field poles, okay, so your field poles that are rotating, and a stationary armature, or a rotating armature and stationary field poles. So there's a relationship there between armature windings and your field poles. Okay, so we will have to make a note of that at some point, right? But for now, this is just to familiarize ourselves with the subject matter. So here goes. Synchronous machines are, however, invariably constructed with a high power armature winding on the stator and low power field winding on the rotor. Synchronous machines are, however, invariably constructed with a high power armature winding on the stator. Okay, so when we talk about armature winding, it's referring to what's on the stator, okay, and low power field winding on the rotor. So now when we talk about field windings, we are referring to the rotor in this context. When we are referring to the armature, we're actually referring to the stator. So armature, stator, stationary part, field windings, it's on your rotor, your rotational part. So that also gives us clarity, that gives us a better or a deeper insight into properly viewing the creature that we are dealing with here, called synchronous machines, or in this case synchronous motor, synchronous generator, it depends, right? There are two types of synchronous machines depending on the geometrical structure of the rotor. There are two types of synchronous machines depending on the geometrical structure of the rotor. Two types of synchronous machines. So there's synchronous machines, and in this case there's two types of them. And the type of synchronous machine, it is dependent on the geometrical structure of the rotor. Okay, these are the salient pole. As a parenthesis, we can define it to be as projecting or standing out poles. These are the salient poles. And cylindrical rotor synchronous machines. Okay, so there are two types of synchronous machines depending on the geometrical structure of the rotor. Now, when you want to define it, you define it in terms of salient pole. What is a salient pole? It simply means projecting or standing out poles. Salient poles, the poles are projecting out. Okay, right. Or you have your cylindrical rotor synchronous machines. Okay, now let's continue. The field winding on the salient pole type is a concentrated winding, meaning that it is wound on the pole in the form of a bobbin. Okay, in the form of a bobbin. In this case, now what is a bobbin? A bobbin, it's actually something people who normally do sewing, they use what is called a bobbin. A bobbin is just basically where you take thread and it's tightly wounded, yes, on a small cylindrical piece of metal. Okay, normally you would have the roll thread, okay, and then you would have the small version, okay, and then that smaller version, it's actually called a bobbin. Bobbin is just basically this small cylindrical piece of metal with thread wounded tightly around it. Yes, that's what we refer to as a bobbin. Okay, so the field winding in the salient pole type is a concentrated winding, meaning that it is wound on the pole in the form of a bobbin. In the case of a cylindrical rotor type, in the case of a, okay, so now they are distinguishing. We are distinguishing. In the case of a cylindrical rotor, okay, remember you have your salient pole, and then you also have what is called your cylindrical rotor. So here they actually distinguish between the two. That's why they say the field winding on the salient pole. It's referring to the salient pole type is a concentrated winding, meaning that it is wound on the pole in the form of a bobbin. So that's salient pole type. Then you also have the cylindrical rotor type. The field winding is a distributed winding housed in slots. Okay, all right. So this thing of salient pole rotor, it's actually something worth looking into. Salient pole rotor. Okay, right. A salient pole rotor is used in hydropower stations and is driven by means of Pelton wheels and Francis turbines. Okay, my mechanical engineering friends, they will know a lot about Pelton wheels and Francis turbines. Yeah. Okay, hydropower stations. Okay, that's nice. That's interesting. The rotor has between 2 and 40 poles. So that's speeds between 3,000 revolutions per minute and 50 revolutions per minute that can be obtained. Okay, the winding is of the bobbin type and is called a concentrated winding. I mean, that's exactly what I said earlier about a bobbin, right? So if you think concentrated winding, just think bobbin. And then, yeah, and if you think bobbin, just think salient pole rotor. And if you think salient pole rotor, then you should also think cylindrical rotor machine. Yeah, because there's your salient pole and then as well as your cylindrical rotor types of machines, yes. Not types of machines, but substructures, yes. Okay, now let's look at the cylindrical rotor. All right, we are going to look at a cylindrical rotor, cylindrical rotor, cylindrical rotor, cylindrical rotor. Now, when we say cylindrical rotor, okay, what we have to realize is there's two of them. There's what? There's a salient pole, that's the one we just described. So now we are switching over to cylindrical rotor. Okay, right, so now cylindrical rotor. It is found in steam driven power stations, which means that the alternator is driven by means of a steam turbine. The rotor, it usually has 2 poles and very seldom 4 poles. The speed that can be obtained are 3000 revolutions per minute and 1500 revolutions per minute at 50 hertz. The air gap is uniform and the rotor has a small diameter and is axially long. That means this pen is what? Axially long, meaning along the axis it is long. That is essentially what it means. Okay, normally along the diameter it would be long, but in this case it's long against the the axis. Yeah, axially long or axially elongated. Okay, the gap is uniform and the rotor has a small diameter and it is axially long. The windings are housed in slots in the rotor and the windings are concentric, okay, and distributed in 2 or more slots. The windings are housed in slots, okay. Slots is just basically those gaps. We refer to them as slots in the rotor, meaning the rotational part and the windings, okay. Your copper conductors are concentric. Now, what does concentric mean? Concentric, it just basically means that they are wounded in a equally spaced circular form. Yes, it's basically circles with equal space. We call it concentric. Yes, at least that's my understanding of it. And distributed in 2 or more slots. Okay, that means you have this axis, and then obviously this axis, it will have grooves, otherwise known as slots. And then in this case here, it says that your windings are concentric and distributed in 2 or more slots. That means one groove is one slot, another groove is another slot. So those 2 grooves or those 2 slots, they give you 2 slots. And in this case, it says 2 or more slots. Okay, right. That's the rotary part. The DC is supplied to the rotor by means of slip rings. I mean, that part is obvious. This thing, if it's rotating, how else are you going to get DC in there? The only way is with slip rings. Okay, right. This sets up a magnetic field that cuts the stator conductor. The stator conductor, it's as the name says, it's the stationary part, right? And it induces an EMF in the stator. Okay, and this is your cylindrical rotor. Okay, right, and now let's continue. A further distinction between the 2 types is that salient pole synchronous machines, they have what is called a non-uniform air gap. Non-uniform air gap, simply meaning the spacing of the air gap, it's not concentric. Concentric meaning it's not of equal size. The gap here and the gap there, there's differences, at least according to this, but it's definitely not uniform. Okay, under the pole centers, okay, the air gap is minimum, and between the poles the air gap is maximum. Under the pole center, meaning the center of the poles, the air gap is minimum, okay, and between the poles the air gap is maximum. Okay, in cylindrical rotor synchronous machines, the air gap is uniform throughout, neglecting the slot openings. The rotor of both types of machines are similar to the induction motor stator. The rotors of both types of machines are similar to the induction motor stator. Now, when we refer to an induction stator, here's your induction stator. Here they say the rotor of both types of machines are similar to the induction motor stator. Okay, in other words, the synchronous machine consists of a cast iron stator frame, a cylindrical, laminated and uniformly slotted core, a polyphase distributed winding, placed in stator slots, bearings, and a base. Okay, as in the polyphase induction motor. The stator frame, the stationary part, that frame, and the end covers merely serve as mechanical support to the stator core. The stator core is the stationary part and are not designed to carry the magnetic flux. Now that part should be obvious because those things, they are made out of cast iron, and there's no way cast iron can enable you to induce a magnetic flux or a magnetic field or anything of that sort. It's, from my understanding, it's non-magnetic. Okay, so now let's continue. The frequency of the generated EMF, the frequency of the generated, now this is within the context of a generator, because now here they are talking about generated EMF. F is equal to NP, where N is the revolutions per second, and then P is the number of pole pairs. So simply meaning, if you manipulate the revolutions, meaning the speed, the rotational speed, directly, you'll be manipulating frequency. If you, well, this should be common sense, but if you manipulate the number of pole pairs, then directly speaking, you'll be impacting or influencing frequency. Okay, now oil engines and hydraulic turbines operate best at relatively low speeds. Oil engines and hydraulic turbines. Hydraulic turbine. What is the hydraulic turbine? I don't know what hydraulic turbine is. I have an idea of what it could be, but I don't know within this context. Oil engines and hydraulic turbines, they operate best at relatively low speeds. Okay, therefore, the alternator driven by these prime movers, oil engines and hydraulic turbines, okay, alternators driven by these prime movers must have a relatively large number of poles. Why? Because you want high frequency. I mean, the moment you say large number of poles, I'm thinking high frequency, right? For accommodating a large number of poles, the rotor diameter must be comparatively increased, because I mean, the more pole pairs you have, obviously your diameter, in this case your rotor diameter, it has to increase to accommodate all of that. Okay, must be comparatively increased. And from a mechanical consideration, salient pole construction has been found to be best suited for low speed prime movers. Salient pole construction has been found to be best suited for low speed prime movers. Salient pole rotor structure is also used for comparatively small synchronous machines. Salient pole rotor structures. So when we look at salient pole, first of all, let's look at salient pole construction. Just salient pole, okay? Salient pole construction, it has been found to be best suited for low speed prime movers. That's salient pole constructions. Now when we look at salient pole rotor structure, it is also used for comparatively small synchronous machines. For larger machines, the laminated salient pole types are bolted to the spider keyed to the shaft, okay? Right, so keyed is just basically, you have one thing, let's say you have a shaft, let's say you have a bore going over your shaft. The bore will be able to move around. So when you key something, it's to ensure that there's no moving around, that it moves as a unit, as one. So that's what they basically mean here. Salient pole rotor structure is also used for comparatively small synchronous machines. For larger machines, what type of machines? Salient pole rotor machines, okay? For larger machines, the laminated salient pole types are bolted to the spider keyed to the shaft, okay? Damper bars are usually inserted in the pole shoes, okay, to damp out the rotor oscillations. Okay, rotor oscillations, right? The pole shoe, obviously rotor oscillations, that's something we will discuss hopefully later on, but for now, it's actually type of vibration, but yeah, vibration, oscillation, it's within the same vicinity. But yeah, the pole shoe of a salient pole is suitably shaped so as to obtain a sine wave for the radial flux density in the gap. The pole shoe of a salient pole, it is suitably shaped so as to obtain a sine wave for the radial flux density in the gap. Commercially, the Salient pole machine synchronous alternators are also called hydro alternators or hydro generators. Commercially, that means within the sphere of energy generation, obviously in the context of profit. The Salient pole machine synchronous alternator, it's also called a hydro alternators or hydro generators. Okay, steam and gas turbines have the best operating characteristics at relatively high speeds. Okay, steam and gas turbines have the best operating characteristics at relatively high speeds. Alternators driven by these turbines must therefore have a fewer number of poles, say 2 to 4. If salient pole construction is used for such high speeds, the rotor structure, if salient pole construction is used for such high speeds, the rotor structure may not be able to withstand the enormous centrifugal forces developed by the salient pole machines. Therefore, cylindrical rotor machines would be better suited for this type of operation, considering the mechanical restraints. Commercially, cylindrical rotor synchronous alternators are called turbo alternators. Okay, synchronous motors, usually of the salient pole type, are of the same general construction as salient pole alternators. Under steady state, the synchronous motors operate at a constant speed as determined by the frequency and the number of poles. Okay, in salient pole motors, the function of the damper bars, now damper bars, it's basically along your axis, the axis of your axial, if I may put it as such, or your shaft. Yeah, it's along the axis of your shaft. Yeah, another person would say it's parallel to your shaft. Yes, around. Yes, so that's basically when we talk about damper bars. Yes, in salient pole motors, the function of the damper bars are to damp out the oscillations and to start the synchronous motor. Now, when they say in salient pole motors, first of all, what is a motor? A motor, it's a thing that reduces rotational force, okay, or rotational motion. The function of the damper bars, blah, 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 blah. At a later stage, hopefully, if we get there, we might never get there, but yeah, that is basically to enable your synchronous motor to, for that specific point in time, to function as a squirrel cage type of motor. In this case, let's not say squirrel cage. Squirrel cage is actually the most accurate way of phrasing it, but for now, let's just say induction motor. Okay, because what happens with your induction motor is, with your induction motor, you have a rotary part and you have a stationary part. So your stationary part, it's going to create a rotating magnetic field, and then that rotating magnetic field is going to induce currents in your rotary part. And then by inducing currents, what's going to then happen is, then it's going to start, this is not the complete principle of operation, but it's a summary, because the topic here, it's not necessarily induction motors. The topic here is to basically explain what we mean when we talk about damper bars, according to what I know. Okay, it's basically, then you have those bars, they then serve as a type of squirrel cage, and then that currents now will be induced because of the cutting magnetic field, and then because of that, now it's going to start rotating. Okay, and then as it starts rotating, what is then going to happen is, then that rotational part, okay, which in this case is your rotor, it will, because of slip, it will then rotate, and as it rotates, it's going to be something like what, 90%, 95% the speed of the stator or the stationary part. Okay, remember, with your stationary part, you have windings, and then those windings, they create a rotating magnetic field. Let's say the rotating magnetic field, let's say the speed is 10, then the speed of the rotary part will be 7, 8, 9, but it's definitely not going to be 10. Okay, and then this action, it's basically why we have the damper bars there also, or at least I'm speaking under correction here, but from my understanding, yes, you have these damper bars, and then if you look at a squirrel cage, it also has type of bars, hence the name squirrel cage. Okay, and then yeah, for synchronous machines or large sizes, adequate cooling arrangements must be incorporated to dissipate the heat produced by the various losses. For synchronous machines of large sizes, adequate cooling arrangements must be incorporated to dissipate the heat produced by the various losses. That's for large machines. Okay, this is also something that's true in energy generation power plants. Yes, not energy generations, power plants. Yeah, energy, let me not say energy generator plants. Yes, for relatively large sizes, closed circuit cooling using air, water, hydrogen, or helium is often used. A synchronous machine is usually connected to an energy system fed by other alternators. A synchronous machine, it is usually connected to an energy system that is fed by other alternators, simply meaning you have these sub-alternators that actually feeds into your, what we would call a synchronous machine. Okay, what are they feeding? They are feeding energy. Okay, in a synchronous alternator, simply meaning a synchronous type of machine that is generating power. Okay, the frequency of the generated EMF depends on the rotational speed and poles. Okay, right. Thus, a synchronous frequency of the generator, thus a synchronous machine can be connected to an energy system only when frequency or the rotational speed of the synchronous machine is equal to the frequency of the supply system. In other words, for successful operation, the rotational speed of the synchronous machine must synchronize with the frequency of the system. This is why it's called a synchronous machine. A single synchronous machine may operate at any frequency or speed since it is not synchronized with any energy system. However, a single synchronous motor fed from an energy system must synchronize its rotational speed with the system frequency. Okay, I'm going to just read that last part again. For synchronous machines of large sizes, adequate cooling arrangement must be incorporated to dissipate the heat produced by the various losses. Okay, for relatively large sizes, closed circuit cooling, okay, using air, water, hydrogen, or helium is often used. Okay, a synchronous machine is usually connected to an energy system fed by other alternators. A synchronous machine is usually connected to an energy system fed by other alternators. What is fed? The energy. Okay, in a synchronous alternator, the frequency of the generated EMF in a synchronous alternator, simply meaning a synchronous generator, in a synchronous generator, the frequency of the generated EMF depends on the rotational speed and poles. Rotational speed and poles. That's your N and that's your P. Yes. So that's your N and that's your P, rotational speed and poles, and that obviously gives you, but the frequency of the generator depends. That's exactly what F equals NP means. N is your rotational speed and then P is your pole pairs, your number of poles. Okay, so your synchronous generator, that's the case. That's how you actually determine frequency. Thus, a synchronous machine can be connected to an energy system only when frequency. Now, this is why frequency is important. A synchronous machine can be connected to an energy system only when frequency or the rotational speed of the synchronous machine is equal to the frequency of the supply system. Simply meaning, for you to get, let's say, some sort of 50 hertz output, you need to have some sort of 50 hertz input, something of that sort. That's what they mean here. Okay, in a synchronous alternator, okay, right, the frequency of the generated EMF, it depends on the rotational speed and poles. Thus, a synchronous machine can be connected to an energy system only when frequency or the rotational speed of the synchronous machine is equal to the frequency of the supply system. That's exactly what I just said. In other words, for successful operation, the rotational speed of the synchronous machine, the rotational speed of your synchronous machine, it must synchronize with the frequency of the energy system. Energy system is the system supplying the energy. At least that's how I understand this to be. Okay, this is why it's called a synchronous machine, because they have to synchronize. Okay, a single synchronous machine may operate at any frequency. A single synchronous machine, it may operate at any frequency or speed. Single, since it is not synchronized with any energy system. However, a single synchronous motor fed, now this is a synchronous motor, meaning you are now feeding it energy, fed from an energy system, must synchronize its rotational speed with the system frequency. What is the system frequency? It deals with your supply line.